welcome to part 2 of lecture 27. I just want to give you a very rough idea of how to choose the elements. Again, the Abacus user manual is your friend, so please, whenever you are in doubt, check out some of the documentation. I would say the first choice would be quadratic reduced integration elements. So, for plane strain or plane stress or for 3D, so the CPE8R, that's the continuous plane strain formulation, quadratic with reduced integration, CPS8R, that's the plane stress, quadrilateral with reduced integration, and C3D20R, that's the hexahedra, so that's the 3D cube with 20 nodes with reduced integration. Unless you have large strains where you have unstable modes, then maybe you want to be careful with the reduced integration. But if you have, for relatively well-behaved problem, these elements, these quadrilaterals or cubes with reduced integration will work. As I said, if you have very large strains or you have some complex interactions such as contacts, or you have sharp corners or single point forces or node-to-node constraints, then these problems have singular stress solution. I showed this last time. So if you had this 90-degree corner, then it doesn't matter if you use quadratic elements. Your convergence is given by the fact that you have this 90-degree corner. So then you can use quadratic, but it will give you the same convergence as if you use the linear elements. So just be careful. But if your problem is nice, your geometry is nice, you don't have modes in which you can maybe have these zero energy modes of reduced integration elements. So if your strains are moderate, then these quadratic reduced integration elements will be fine. So for regions where you have stress concentration, where your stress is changing a little bit more rapidly, then use full integration. Again, quadratic elements are a pretty good choice, unless the problem is dominated by a singularity. And what type of singularity am I talking about? Where you have these node-to-node constraints, you have these sharp 90-degree corners, you have contact. So in those cases, your convergence might not be driven by the shape functions. So in that case, it doesn't really require you to use quadratic elements. But if your problem is, quote, nice, then you can use quadratic elements. And then, as I said, depending on how much the stress is varying, you might go for the reduced integration or you might go for the full integration. For large deformations, the nonlinear geometry, we didn't cover this much in class, but depending on how much distortion, you might be better off with the linear elements. Again, quadratic elements are more accurate, but one of the disadvantages of the quadratic elements is that their performance depends on whether or not the shape is regular. So by this high quality, I mean they have to be nice meshes, regular shape. But as they become as the element becomes distorted, so you have very large deformations and the elements become distorted, the quadratic elements are not as robust for these changes in geometry. So you might have that your Jacobian becomes negative. You have problems with the numerical integration. So that's one thing that can happen with the quadratic elements. That if you have very large deformations, then the quality of the solution goes down. So in that case, you might be, unless you refine a lot, you might be good with the linear elements. So that's just, again, something to keep in mind. The quadratic elements will work really well when you have, some deformation but just not distorted elements. That's the problem with the quadratic elements, is the level of distortion of the elements. Again, linear elements are more robust when distorted, but you need finer meshes. So there's always some trade-off. When you use reduced integration, beware of some unstable patterns of the solution. We have talked about this in class. There's some zero energy modes for reduced integration that lead to some hourglass shape deformation of the elements. Yeah, so that's just something to keep in mind. Like, try to look for the patterns. I had some slides, maybe a couple of classes ago, where I showed more of these unstable patterns that you can find. So just keep an eye open for those. Um, what types of elements we have really pushed for the use of the quadrilaterals or hexahedra, so the bricks in 3D, whenever possible. So if you can have a structure mesh with quadrilaterals or with cubes, then do that. Now it's more difficult to get meshes with this type of elements, and in some cases it's close to impossible. So in some cases you might have to end up using triangles or tetrahedra. Now the problem is that these um, these elements, these triangles and tetrahedra, are stiff numerically. So they have less degrees of freedom compared to the quadrilateral and the brick elements. So what this means is that actually you need a lot finer meshes to get a good solution from these elements. So you can use them. Just keep in mind that you probably need finer meshes if you use triangles and tetrahedra. And then in some cases you might be able to get meshes for the quadrilaterals and bricks. In some cases, if your geometry is very complicated, the figure that I have here, it's a cube of tissue with a vessel network. This is very intricate geometry, so then really the only way of meshing this is with tetrahedra. So we use quadratic tetrahedra, for example. Again, just keep in mind that if you do a convergence analysis, you'll probably find that if you use triangles and tetrahedra, you need finer meshes. Another one, uh, definitely do not mix different polynomials. So you cannot use linear and quadratic elements. And this relates to the conditions on the completeness and continuity of the shape functions that we briefly talked about. So all your shape functions should lie in the same space. So if you're using linear elements, all of them should be linear. If you're using quadratic elements, all of them should be quadratic. Do not mix different order of the elements. You can mix full and reduced integration, that you can do. You can mix different elements of the same polynomial order, so you can have linear triangles with linear quadrilaterals, that's fine, or you can have linear tetrahedra with linear hexahedra, that is fine, as long as they have the same polynomial order. So quadratic with quadratic of different shapes, that's fine. Mesh in a way that you increase the number of nodes near regions with high strain gradients. Use bias in the meshing. We talked about this for the plate with a hole. There's no point in refining the mesh in the far field because the solution is very, very smooth. The strain changes very slowly. However, near the hole, you have these really high strain gradients. So in that part of the mesh, you really want to have a fine mesh. Check for the quality of the mesh. The more regular the elements look, the better. So for example, here there's just one illustration that shows sort of a skewed mesh, and then a better mesh would look like this. So the more regular the mesh looks, the better the approximation. Monitor the distortion if your elements, if they, and this is particularly for the nonlinear geometry problems, beware of element distortion. As I said, when the elements become distorted, the approximation becomes worse. So you have to keep an eye on that. Like this is an example of how to use bias in the meshing. Again, in the far field, there's no point having a fine mesh, but in the regions where you have higher stress gradients, then you need to have finer meshes. So use bias to do that. You can use adaptive meshing. Abacus has some capabilities to do that, where you start with some regular mesh and then it will refine the mesh according to this to the gradients. There's some error approximations that Abacus can do to try to find where to refine the mesh. So that's something we haven't done, but that's something you can do. But again, you don't need to have a fine mesh everywhere. You can have just a fine mesh in the region where you need it. Another thing that I said last lecture as well is that whenever possible, you want to simplify your problem. Instead of doing the 3D elasticity problem, you want to do plane stress, plane strain that we have talked about, or an axisymmetric problem. So Abacus has some capabilities of doing this. So you can use axisymmetric elements. We didn't really talk much about them, but they are in Abacus. Yeah, this is just one problem from the Abacus documentation. Again, these type of examples are in the Abacus manual. So if you have a problem that you know that is axisymmetric, but we haven't talked about that in class, go to the Abacus manual and try to look for an example of an axisymmetric problem so you can see which are the elements that have the notation for the axisymmetric formulation. Contact problems, we also didn't cover that in class. There's a couple of ways of doing that with the penalty method or Lagrange multiplier. Again, you can probably look at some of the documentation in Abacus. Yeah, I think most of the times you just need to create the interaction. Again, linear elements might work better for these contact problems. What other thing? And then coupled problems. We didn't talk about this, but I don't know how much Abacus can do on this. But you might have, I guess, for the future problems, you have fluid structure interaction or thermomechanics. That one definitely Abacus can do, or any combination of PDEs. Not Abacus. There's this other commercial software called COMSOL, and that one can do different types of PDEs at the same time. So just something to keep in mind. I think that's it. Yes. All right. So that's sort of the overview of a few tips on how to select elements and what can you use the finite element method for.